Hello and welcome to this PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Please remember that you can ask questions anytime if you're joining us live. You don't have to wait for the Q&A section at the end. We'll queue up those questions and ask them when it's time on your behalf. If you let us know where you're joining from and perhaps which student asked the question or what grade your class is, any identifiers like that, we would be happy to give you a shout out when we ask your question. So today's guest is Dr. Robert Smith. He is a professor in the Department of Mathematics at the University of Ottawa. Thank you so much for joining us today, and I'll let you take it away.
All right. Well, thanks for having me. I think the Partners of Research is great stuff, and I'm very, very pleased to be a part of this today. So for those who don't know, I'm a mathematician. I'm a professor at the University of Ottawa, and I use mathematics to study disease. So for me, mathematics, I guess, is a tool. It's a very, very powerful tool. It's a rigorous, dense tool sometimes. It's like a very, very tough language that you have to learn. But when you learn a language, you can do all kinds of things with it. And you can speak, you can communicate, but you can also do amazing things like write poetry and so on. So I think of math as being very similar to a language in that way. And for me, math is something I want to use in order to study problems of infectious diseases. And so I do serious diseases like HIV and malaria and so on. I also do fun diseases, if you will, like zombies and beaver fever and a few other things that we're working on. So I thought today what I would do is just sort of show you, I guess, the outline of how it is that you would model a disease using mathematics. And so I'm going to choose a disease you probably don't know of. It's called Guinea worm disease. So I'm just going to share my screen here. Okay, so this is Guinea worm disease is a fairly obscure disease, but the reason it's interesting, I think, at the moment is you're probably going to hear a lot about it in the future because it's almost certainly going to be the next disease to be eradicated. So we've had a very, very bad success at eradicating diseases. We've eradicated only 2 diseases in the whole of human history. One is smallpox, and the other is a cow disease called rinderpest. So of all the human and animal diseases, we've eradicated 2. But very soon, I think we're going to hit number 3, and that's Guinea worm. So Guinea worm disease, I'll put the life cycle here. This is a disease in the drinking water. So as you can see, when you drink the water, so what you're drinking is you're drinking some, essentially there's a flea that lives in the water, and there's a parasite that lives on the flea. And so, well, it actually lives inside the flea. So the parasite is inside the flea's stomach. You drink this tiny flea that you don't even notice is in there, or it just looks like a bit of dirt or something. And then it goes down, and in your stomach, the stomach acid dissolves the flea, and then it leaves the parasite. And the parasite tends to travel down. And so you can see here, it goes down into the foot a lot of the time. And so this parasite lives in your foot, and it grows over about a period of a year. It grows into a worm. And so you have a worm living in your foot. And what happens is your foot is burning and itching, and you have to put it in the water. So when you put it in the water, then the worm bursts out, and it releases thousands, sometimes millions of parasites out into the water. So of course, that restarts the whole cycle. And so here's a picture of actually the worm that's living, and so I apologize for the intenseness of this picture, but I think it does give you a good visual. And the way that you get the worm out is that actually, as you can see here, you roll it up on a stick. So it's a little stick that this person is using, and you roll the worm. Now this worm is largely emerged. It starts off just with a little head poking out, and so you have to very, very slowly, you essentially wind the worm around the stick, and that inches it out, what, a centimeter or 2 per day. So it takes about 2 months for this worm to come out of your foot. And you can't pull it out because if you pull it out, it breaks off, and then you get infection, and then it can be very serious. So you could do it with surgery, but of course, most places where this worm is don't have access to this kind of surgery. So this disease was very widespread during the 19th and 20th centuries. It was all through so the middle parts of Africa. It was in the Middle East. It was in Asia, and so on. So we had Southern Asia, the Middle East, Northeast, and West Africa. And there were about 50 million cases in the 1950s, and today it's almost gone. And so the question is, why has this disease gone? And it's not by chance. It's because, well, actually, one person decided to get rid of this disease. And it's a person you might have heard of, although he's a little bit older now. In fact, it's former President Jimmy Carter. So he was president of the US in the 1970s, and after he was president, he decided he would get rid of a disease. from the planet, I guess, as you do. And and he was basically successful. There are now less than 25 cases of Guinea worm disease. That's down from 50 million in the 1950s. So this is an astonishing achievement, actually. And what you see here is the decline, and this is excellent data. This is almost exponential decline. It's very, very consistent, and this data goes up to 2007, but actually the recent numbers show it's continued down just in the same way. The only blip here actually is where they just essentially remeasured what they were doing. There were countries they couldn't reach, and so they now included those in the mid-90s, but basically you can see that the same thing happened after that. Okay, so how do we model something like this? So here is essentially the way you do a mathematical model. You do it as a picture. And so you start with people who are susceptible. So these are people who do not have the infection. And those people can become infected. But when they're infected, so they have the parasite in them that's growing inside their foot, they're not infectious. So they're not able to infect other people during this time, but they are themselves infected. And they may, of course, be infected by more than one parasite at a time. You can have up to 7, people have seen up to 7 at any given time. And then when the worm bursts out, you become infectious. And so now you don't infect people directly, but you infect the water. So that brings you into the waterborne parasite here. And so then the waterborne parasite then gets drunk by people, and that's how the cycle goes. Now the people themselves, when they've stopped being infectious, they return back to being susceptible. So these sort of compartments are essentially the building blocks for the model. So we have an infection rate, which basically tells you what are the chances that you drank the water with a parasite in it. There's the parasite birth rate. So this is the number of parasites you get ejected from the person to create a new I guess, infection in the water. And there's the rate at which you sort of, I guess the parasite bursts out of your foot. So the rate of developing active infection. So you're already infected, but you're not infectious. So this alpha is the rate at which you become infectious. And finally, there's the recovery rate, which basically means your worm is done. It's done the infecting. Of course, the worm may still be in you, but it's the rate at which you return to being a susceptible person. So what we can do then is write equations. And the equations that we write essentially tell us how things change. So on the left-hand side of the equal signs, we have differential equations, which are derivatives. So these are essentially a rate of change. And all you need to know about a rate of change is what comes in and what goes out. So for our susceptible individuals, people are born. That's the way you make a person. Of course, you can be born. Or possibly you move in from somewhere else. And then you leave when you're infected. So this is when the humans... the susceptible people meet the parasite. So I guess the humans meet the parasite, and there's some chance of infection, and you leave this class and you go into the infected but not infectious class. You can also die from background reasons. So in every class, there's a minus mu term here. So everybody can die, but you don't die from the disease. The disease is not a killer. So this is just dying from other reasons, which takes you away. And this last term in the first line is returning from infection. So people who are infected but not infectious, they came in from being infected, and then they leave by becoming infectious, so they move to a new class, or they leave from death. And infectious people, they became infected because the parasite burst out, and then they leave when they recover, and so this recovery term is what brings you back into here. And then they can leave by background reasons. And this is the parasite, and the way the parasite changes is the parasites come in, there's some number of parasites produced per infected person, and they leave by death. They actually die quite quickly. They don't live very long in the water. So that's why they produce thousands and sometimes millions of parasites, because they have to infect people very quickly. And so what you see over this far side is this is all when certain times are not true. So this is most of the time, this is what's happening. And then occasionally at certain times, we apply an impulse. And so this is chlorination. This says that there's a different kind of a change. There's an instant change in the parasite, which is we're going to decrease the parasite. And that's when we put in chlorination. And so our chlorination will reduce the parasites by some proportion R. And it's done at certain times. And these times might be regular or they may be not regular, depending on how much chlorine you have available, depending on resources, depending on infrastructure, and so on. So we can do some mathematical analysis. I won't go into too many details, but I'll just say one of the things we might want to do is overestimate what's happening to the parasite. So this is the previous equation. We changed it a little by estimating how many humans there are in different cases and say now we have an overestimate. And the reason we want an overestimate is because that becomes much easier to solve. And so usually you can't solve these equations because each equation depends on other equations. But this one now only depends on W. So all the other variables in here, they're not really variables, they're just parameters. These are just numbers that I happen not to know right now, and I can go and measure these in the field and fill them in. So now I have a single equation, and this single equation is just for the parasite, and we can solve that. And you can solve that because it's a recurrence relation, essentially. So what's happening is, if you look down in this diagram here, the parasite is growing, and then we chlorinate, and so we reduce the parasite, and then we let the parasite grow for a while, and then we chlorinate again, reducing it, and then it increases and so on. And you can see that we're approximating the chlorination by an instant change. And that's a handy way to kind of think about something that's not quite instant, but it's very short. So the amount of time it takes to pour in chlorine is very, very short compared to the time between chlorination events. So I'm going to say, I'm just going to approximate this change in the parasite numbers by a jump down or a shock that happens to the system. And it just makes life pretty simple, because what I really then can look at is the endpoints. If I look at the maximum parasite here versus the next one, I can solve some relationship between the two. And that's what this long equation is here. And you'll notice this depends on the various times. Those times might be regular. So in this diagram, they look fairly regular here, but they might not be. And if they are regular, then I have constant chlorination. And so I can solve that explicitly. So now I can find the limit in the long run of what's the sort of local maximum of parasites. How many parasites are there just before a chlorination event if I do a lot of chlorination? And I can find that exactly, and that's this complicated thing here, but it's not that complicated in the scheme of things. So what I can say is, if I want the parasites to be under a certain level, so if I'd like to control the amount of parasites in the water, I could find the best times to do it. So this tau here is the times between chlorination. So if I rearrange that, essentially I just solve this equation for this tau, then I can find the maximum amount of time between chlorinations. And so this thing here, although it's got, it's got a logarithm and it's got some complicated parameters in here, I can give this now to public health officials, and that's something that they can solve themselves. So they can put their numbers in. They can find alpha and pi and gamma and so on, and you can specifically measure how effective your chlorine is. So that was the R here. How low you would like the parasites to be, and then you measure the death rates, the recovery rates, the infection rates, and so on. But most of these things are just things from the biology. And so now you can give people this one and say, well, given the things you do know, what don't you know? You don't know how often you want to chlorinate. And so that gives us an idea of how to chlorinate, how often we'd like to do it, if it's regular. If it's not regular, we can do a similar thing, although it's more complicated. And this will keep it below a certain threshold. But I said at the beginning that we're not actually looking at below a threshold, we're looking at eradication for this disease. So one of the other things we can do is a sensitivity analysis. And what we've done here is these are called partial rank correlation coefficients. So essentially what this does is it says we take an output variable, and our output now is the number of secondary infections. This is how many people are infected per infected person. So essentially, once we go through the whole modeling cycle, how many infections will I create if I was infected? And so what we're measuring here is the variation of every key parameter that has an impact on that. And you can see that the most important ones are the parasite death rate, and that's the kind of thing I can control through chlorination, or the transmissibility. So that's the kind of thing I can control through stopping the parasite from getting into a human. So I could do that, for example, using cloth filters. I could filter the water. I could stop people drinking, essentially, taking in the parasite. And the other one that's important is the parasite birth rate. And that's how many parasites come out of my foot. And so those are the three important ones. And it happens nicely that these are the ones that we can control the most. And so if we alter each of these parameters by a factor of 100, so without any alteration, you can see that we're above the threshold we'd like to be. This is the eradication threshold. And so normally, mostly we'd be up here. If we adjust the parasite death rate, say through the chlorination that we talked about earlier, you can see that the disease is controlled but not eliminated. We're low, but we're not below the threshold on average. Whereas if we control the transmissibility, and we can do that using our cloth filters that will stop people drinking the infected water, and they'll just drink the clean water instead, then we can reduce the average below the threshold. But you can still see that the interquartile range is a little high. So the upper edge of this box, that means about 75% of possibilities are between these two edges. We still have a few up here. But the best one, it turns out, is the parasite birth rate. So if we can reduce the parasite birth rate by a factor of 100, then we can see not just the average, but also the whole interquartile range is below our threshold. So if we plot that in a three-dimensional way, then here is the parasite death rate is along the axis along here. We have the transmissibility up the top, but notice that's on a log scale. And down here we have the parasite birth rate. So each parasite produces about 100,000 new parasites when it bursts out of your foot. So without doing anything, we're sitting here, and we're above this surface. So this surface is the threshold for eradication. And so what you can see is that we'd like to be below the surface. This is the surface, says above it we have disease persistence, and below it we have disease eradication. So if I chlorinated and I reduced the parasite death rate, I would move back along this direction, and you can see that it's very flat along the surface in that direction. So that means I'd have to do a lot of chlorination before I would get eradication. Perhaps I'm not going to reach it even. If I went down vertically, then that would be reducing the transmissibility. So there I might be providing cloth filters to control the disease, and that's fine. Eventually I hit the surface, except the problem is, of course, that's on a log scale. So a log scale means there's a lot of distance between these. This is really masking a lot of effort that would have to be put in. So I can reach that surface, but it's really hard to do. But if I come the other way, so now I reduce the parasite birth rate, then eventually I get into this region where the surface is lifted up. So I actually have a large region of disease eradication. So how can I reduce the parasite birth rate? I can do that through education. So I can teach people about the cycle and say, well, if you're infected and you need to put your foot in the water to release the parasite, don't do that. Don't put it in, or at least don't put it in the same water. If you can provide a separate set of water, say a bucket or a large well or something that does not get mixed with the water in the rest of the village, and we can put all our parasites in there and then dispose of them safely, then we can take those parasites out, because each time you produce 100,000 particles, then reducing this down here is actually not so bad. It means you need some people not to put their foot in the water. And so this is actually something that we could achieve. So that's really just an overview. I will say, if you're interested, you can either Google me. That's probably the easiest way, actually. Or this is my website. If you Google Robert Smith with a question mark, I'll come up very, very quickly, because the question mark makes me very unique. So you can read about either guinea worm disease itself or other tropical diseases. And the one thing I will just note is, see this symbol here, the medical symbol? This is actually the picture of a worm around a stick. This is where essentially medicine had its roots, because having a stick meant I can take your worm out, and that was medicine back in the day, because you rolled that worm out. So I think that's just a little overview of how we might, think about a disease in the first place. Let me come out of this. So essentially that I have a biological problem, which was my disease, and I translated it into the language of mathematics, and so that gave me first my picture, but then my equations, and now with my equations, I can analyze this to come up with some conclusions. And those conclusions sometimes are obvious. Sometimes it might be that, obviously we want to, treat the water in some way or deal with the parasite in some way, but some of them are not obvious. And so the fact that education is clearly the most viable thing was not clear at all. So people thought, well, it's usually Western level things that matter, like vaccines or chlorination or something like that. What we learn here is that actually a sort of soft tool like education can make a massive difference in controlling a disease. So I think that's where mathematics can be really, really helpful. Okay, so I think I've given you a good overview of how we might deal with the disease. I'm happy to take questions.
Well, that was wonderful. Thank you. I think that's quite amazing in an age where there is a big push for alternates to traditional medicine, that there may be solutions like this if we look for them in some cases. So that's quite amazing that mathematics was what got us there. I think, all right, I'll go to a question from our grade 5s at Jenny Elliott in Calgary, Alberta first. They were wondering if the worm could die inside of the host.
Oh, yes. So usually doesn't, because it grows there. That's actually its sort of natural incubation spot. The problem is it can die if you try and pull it out. So if you rip the worm out by hand or something like that, then the worm dies, which you would think would be good, but the problem is then it leads to infections, and that's where it can really damage your foot. And one of the problems with this, of course, is if your foot is damaged and you can't walk, then you can't work, and so it means that you can't go into fields and you can't produce money for either the economy or for your own family and so on. So this has a very devastating impact on a lot of people who really need to be in fields and dealing with animals and so on for their livelihoods. And so it has a huge economic impact as well.
So if you project forward, and I apologize if you did mention this, but is there an estimation of when this eradication may take place, when it'll be complete?
That's a very good question. So the measures of eradication, they always get bumped up. So there's all these big claims, I will eradicate measles by 2020 or something. And as you get closer, of course, it pushes back. And this disease has also been pushed back. This one, I will say, is the closest. I was just looking it up last week, and we were at about 100 cases last year. Now it's under 25. So the push is coming, but you never know. So you never know what, the problem is because it takes a whole year for the worm to incubate. So we may think it's gone, and then a year later it pops up because somebody had a worm in them, and then small random events happen, like that person might put their foot in the wrong well and it gets spread to more people, and suddenly you have 100 cases next year. And so then the whole eradication sort of gets pushed back. This is really the problem with something that's like essentially a random event like eradication. You have to hope that the randomness is on your side. So you hope that the small stochastic events that happen in your favor, not against you. And those are very, very hard to predict. We're very good at predicting sort of large-scale things with large populations, because in large populations, average people do the average things. And although some people, some odd people, weird people may do some weird things, most people are not. And so most people are doing the average thing. But when it comes down to only a few people, they become very unpredictable. So that's where we have to deal with the messiness of the real world. This is one of the things I like about doing mathematical biology, because I think a lot of the times when you use math, it's very precise and it's very rigorous and very idealized. And biology is not. It's noisy and messy and has terrible things like human beings who aren't predictable and won't do what you tell them and so on. And so you have to essentially, I think, use the math to try and understand what those are doing. And that, to me, is a great challenge. That's, I think, a really big challenge of our time.
Right. I would imagine that sort of compliance along with that education would become so important at the end for that one person who just says, oh, it'll be fine, and sticks their foot in the water, and the rest of the village probably gets pretty angry. So we have a question now from Ms. Cornell's grade 6s at Walter Perry Junior Public School. They want to know how you know when the disease is completely eradicated.
Right, that's another excellent question, because you may think you've eradicated the disease because you didn't see any cases, but how long do you not see cases for before it's fully eradicated? And so I think when smallpox was done, it took quite a number of years. You have to go and essentially do a lot of statistical testing throughout the field, and you want to make sure you've done all the things that you need to do. You need to make sure you have a wide enough sample, you've tested in all the typical kinds of places, you've asked the right people, and so on. And also that your information is reliable, so that when people say, no, I've never seen a worm here, they actually know what worm you're talking about. You're talking about the same worm and so on. When we were eradicating smallpox, people didn't know what smallpox was. To them, it was just a thing that all their children got, and the children either died from or they survived, and that's just how it was. And then they had to show them pictures of babies with smallpox. Say, does any babies in your village look like this? And then they would say, oh, right, that thing that we call whatever, it had a different name in that village. And so it was very hard sometimes to sort of track through. There used to be a period where they would wait and say, if we haven't seen any cases in a long time, then we'll declare it eradicated. There's still that period, but that period has gotten shorter because often technology has improved our ability to measure things. But this disease is one that occurs in very remote places, often in war-torn places and so on. It involves a lot of careful searching through the different countries, and every country has its own quirks. And so I think you have to engage with people on the ground to figure out what local knowledge has occurred. But essentially you do surveys and you try and ask for sure and wait. They're very cautious about announcing the eradication of a disease, of course. And so they may say that this looks like it might be. I think Mali, the country in Africa, was just recently declared Guinea worm free. So there they have to wait a while before they're really absolutely sure that it's not. And of course, declaring a country free of the disease doesn't mean it can't come back, because people can just bring it back from a neighboring country or something too. So it's a complicated one. But when it gets announced, which I'm sure it will, in probably, I would say the next 5 years or so, most likely, then it will be very, very sure that it's gone, because this is the kind of thing they don't want to make a mistake on.
Right. So next I have a question from Ms. Heckman's grade 10 class at Subway Academy 1 in Toronto. And they are studying trigonometry and quadratic functions. Do you use these concepts in your mathematical modeling?
Yes, I do sometimes. So for example, if I'm trying to solve a differential equation, sometimes you might want to know what the equilibria are. And the equilibria are where things are in stasis. So for example, one equilibrium is there's no disease, right? So if I have no disease, if you have no disease in your classroom, you will continue to have no disease unless somebody brings it in. So as long as nobody changes, so if nobody goes out of the room or so on, then you have no disease in your room, and it continues that way. And so a long-term equilibrium, of course, is if this never changes. And sometimes when you're solving for an equilibrium, you may find a quadratic equation, and you may solve the quadratic equation, or you may say, well, if I have a quadratic, at least I know there are at most two solutions. There may be no solutions, there may be one solution, or there most likely may be two solutions. And so I can figure out, even if I don't either want to solve or even can solve the quadratic, or I mostly can solve quadratic, but I may not want to just because it sometimes gets messy or it might be very large. But it even just leads me to saying, understanding the nature of the parabola says I know what conditions occur. For understanding stability, sometimes I'll look at parabola where I can solve my quadratic anytime I like using quadratic formula, but I don't actually need to solve it. I just need to know sometimes whether the solutions are positive or negative. And so if I look at that, I might look at, say, the vertex, and I might look at the intercept and say, if the vertex is on the left and the intercept is above the x-axis, then my solutions must be negative. There's no way they can be anything else. And so it's a really neat way of understanding solutions without having to go through the messiness of solving them. Trigonometry is something that, yeah, we use a lot, actually, and anytime we're trying to measure stuff. I mean, I guess probably that one's maybe a bit more likely to be used in the field if people are, trying to figure out which regions to check for eradication and so on. But yeah, I use the sine rule and cosine rules all the time, double angle formulas and so on. These are all things that do come up. A lot of the stuff that I think we learn in high school is stuff that seems very independent. And so you learn a fact and then you learn another fact, and it seems like, okay, what does that relate to the previous one? But then eventually there comes this critical mass where suddenly you have access to all these things that you've learned that now you can assemble together. And that's very amazing, actually, because you're suddenly dealing with a problem. Oh yeah, I know this. This is a trigonometry one, and you go reach for your trigonometry, and then you've solved your problem. And that's very, very pleasing when that works out.
So next we have a question about the disease again from Whitney, Ontario. Can you get more than one parasite in you at the same time? That's Whitney Public School.
Yes, absolutely you can. They've had people with up to 7 at the same time. The reason it tends to go to the foot is only because of gravity. So gravity just sends the parasite down, but it can hang off your arm, it can hang off your leg and so on. And they've had multiple people, with multiple worms. And yeah, there's nothing to stop that. It likes to live in muscle cavities and doesn't really mind where those muscle cavities are. So as far as the mathematics is concerned, we have to worry about that because we're not dealing with like one person or one parasite per person. We're dealing with a sort of conglomerate average. And so we're saying that if you're infected, it means at that moment there's a worm sticking out of you that's sending out parasites. And if there are 2 worms doing that at the same time, the chances of that are pretty small, but it's not 0. And so we can actually account for that. Because you deal with the differential equations, essentially it's kind of a sort of population waveform that's happening. And so I say, well, on average, there's kind of 1 parasite per time, but there's a tail, and there's a long tail that allows you to actually have multiple parasites. And so in theory, you could have as many parasites as you like. It's just the probability of having a very large number is actually quite small. So the chances that somebody has 50 worms in them is tiny, but not ruled out. So now, we never see more than 7, so that's not a big deal for us. But we do include that kind of stuff in there just because we know that you never know what kind of weird extreme events may happen, and sometimes they do.
And as you said, those extreme events become more impossible to, or more important as they could skew, and you have only 25 cases and one of them has 8 worms. That's a lot different than 100,000 cases with one person with 8 worms.
Exactly right. Yes.
So I think I want to wrap up with a few more general questions that we've had come in. So back to our grade 10s at Subway Academy 1 in Toronto. They would like to know your own personal definition of what mathematics means to you.
Right. That's a very good one. So I think for me, mathematics is a tool, right? And I say that as an applied mathematician. I think mathematics on its own can be very beautiful, and I I guess a lot of my studies were in just mathematics for its own sake, and sometimes you can see extremely beautiful patterns and extremely lovely things. But for me now, as a sort of working applied mathematician, as a disease modeler, to me mathematics is something that shines light in the darkness, I would say. So if I have a mathematical model, like my guinea worm model, right, whatever I do to that model, using all the mathematics, as long as I don't make any math errors, this process is robust. This is completely rigorous. This is the power of mathematics, is that I can go from my premise to my conclusion inexorably. So mathematics is the one really thing that we have that can predict the future. It will tell me precisely what will go on. And if I try to do that in the real world, it's messy and noisy, and I don't know which way to go, and it's unpredictable and so on. So math cuts through all that and just solves problems for me in a beautiful, organized, rigorous way. So then I can bring it back to the real world, and now I've solved a problem in life that I could not have solved, at least in any neat way, or even been sure about which direction to go in. Mathematics is the thing that allows me to do that. So for me, that's where math is really, really amazing. And I say that as someone who started as more pure math and then became applied. I see a lot of my students now are starting more in the applied anyway, so they have a kind of broader background in some sense than I did. I loved math. I was really into it and so on. I really liked it. But when I saw how it could be used to actually help people and solve problems in the real world, that to me was what really flicked the light switch for me.
And I would be remiss if I didn't ask. We talked about Bieber fever, and we talked about the zombie apocalypse very briefly. What did your mathematical model indicate for what to expect with a hypothetical zombie apocalypse, or how would people best survive? What were your conclusions out of that exercise?
I think one of the main conclusions, it's actually very similar to diseases. If you have a new outbreak, so if it's zombies or a new disease, you have a small window of opportunity. And in this window of opportunity, you have to strike very fast and very hard. And so for zombies, you have to hit them really intensely very early on. The big problem with zombies is we don't notice they're coming. You see that in a lot of movies, that there's people shambling around and people think they're drunk or something, and before you know it, the zombies have taken over. So we have to strike them before they strike us. That's kind of the key. And the same is true of disease, that when the new disease arises, we have a window of opportunity to deal with that disease. And we often don't go through that window. We dither about what we're going to do, or we don't have the right tools, right? Or this disease may be upsetting in some way, like sexually transmitted diseases people don't want to talk about and so on. So we lose the opportunity in those windows. And so I think zombies are a fun way of showing that diseases are a bit more serious, but that window of opportunity is really important. The other thing to note, I think, though, is that everybody always thinks they're going to survive the zombie invasion. That's not true. Most people are not going to survive the zombie invasion. And like diseases, there's actually not a whole lot you can do. But like diseases, you can fool yourself into thinking there's a lot you can do. And so people, make preparations and so on. The actual truth is most of us are going to become zombies in the first round, right? We will be bitten, we won't even know what's happening, and we'll be zombies. And I think there's obviously it's very appealing to think, oh, I'll be the one survivor, I will be different, I will be unique. But everybody thinks that. And so chances are actually you're going to be one of the hordes of slavering zombies trying to eat your relatives. And that's unfortunate, but that's probably the reality.
So instead of letting that be the takeaway for our audience, that you're doomed to die from the zombie apocalypse, let's go with one more question here from Kingston, Ontario. They're curious about the path that led you here. Were you always interested or good at math? Did you envision yourself as a mathematician, or were you interested in other fields like medicine or social change, or perhaps something else completely?
Yeah, so I was good at a lot of things, I will say, and I didn't really know what I wanted to do. And in particular, I wanted to be a writer as well. And I thought, I really struggled actually. I thought, should I write books or should I do math? And turns out I do both. And so sometimes I write books about math, but I do books about other things as well. So math for me actually became my primary choice, but I was able to do the other thing on the side. I did think about doing medicine at one point, but I wasn't really that into the biology stuff until after my PhD. So that was, I had a whole PhD in math because I was good at math and I liked math. So I got to the sort of math expertise level and then realized I could apply it. And so that to me was my key turning point in my path. But yeah, I was definitely interested in a lot of things. And I think I probably stuck with the math maybe because I was good at it when a lot of other people weren't. And so, math is a difficult subject for sure. And I think there's a lot of people who will do it because it is so difficult. It's a great challenge. It's a fantastic thing to get your teeth into if you really like problem solving. But yeah, I could have gone a whole number of different ways. What I find now is actually that spread of different things. Like I was very good at English and good at math. Now I do a lot of writing about math, and so I write academic articles, I write books, and so on. I bring those skills together, and those are skills that not a lot of people have. So that allows me to bring something, I guess, to the community.
Right, and you mentioned that your graduate students now often take a slightly different path. What are you finding for them as they go, towards the applied math first?
Yeah, I think things have changed in the last sort of 10 years or so. That now there are a lot more opportunities. That if you want to, say, take calculus in first year, you don't just take calculus with everybody else. You can take calculus for life sciences, you can take calculus for business, you can take sort of calculus for math majors, or take calculus for engineers. Well, whatever it is that you're looking at, you can specialize a bit more from the beginning. And so a lot of my students will take, say, calculus for life sciences, which is essentially, it's a little bit lighter in the math and a little bit more involved in real world problems. So then they get more of a flavor of how the two might interface. And so they come to me with much more, I guess, expertise and maybe more intuition about how to apply math to life problems and so on. For me, I did a minor in physics, and so I was applying it to systems on a pulley and things like that, and frictionless motion and things. But that didn't sort of set me on fire, whereas I found that the biology did set me on fire. And so now there's more options for people to do that. I think there's more recognition that interdisciplinarity is very, very powerful, and we can learn a lot by crossing disciplines.
And do you find yourself collaborating with many others who need perhaps, a lower level of expertise with the math, but still need to have a background there and are doing something else primarily?
Yes, all the time, actually. I love collaborating, particularly. One of the reasons I'm in Ottawa is because the Public Health Agency of Canada is here. And so essentially the Canadian version of the CDC. So obviously health is provincial, but the Public Health Agency can make advisements across all of Canada and synchronize things. So I often work with people who are not particularly math fluent, if you like, but I need them to be at a certain level. So often I teach them how the model works and how they can create the model, or I teach a course, for example, where it's half mathematicians and half biologists. And so the math people know nothing about the biology, or very little, and the biologists know not much about the math. And so they work together and they come up with projects together. This is how the zombie stuff started. This is how the beaver fever stuff started, was people sort of essentially mixing in like this. I'll work with government people and so on. I don't need them to do the mathematical analysis themselves, but I need them to sort of understand what's happening. So I need them to engage at a lower level, for sure, but not necessarily the high level. And that's actually a really good hybrid, because if we can have a conversation about the model, I build my model and they say, yeah, okay, you've put your parasites in, but what about, earthquakes? We need to put earthquakes in the model and you don't have it. So they need to be able to see that it's not there. And then if they think it's important, then I can go away and put that in, come back with them and have a conversation. What do you think now? They say, okay, yes, you put this in. Then I can go away and analyze it and decide, do earthquakes matter or not? Right? And probably with earthquakes, they don't matter much, but maybe occasionally they do. And so you can then go investigate those problems. And I've had a lot of success in working with people and doing that kind of thing, where we can go away and do the high level math and come back and have conversations with them about what's happening. And sometimes you go around this cycle a few times where you keep changing the model with different requirements.
It sounds like a lot of conversations back and forth to narrow in and finally get the results you need. But unfortunately, that is all the time we have for today. Thank you so much, Dr. Smith, for joining us, answering our questions, and sharing your expertise.
Yes, well, thanks very much for having me.
And next up on PIR Live event, we are talking about astrobiology and the Curiosity Mars rover. More information on this and other upcoming PIR Live event webinars is available at pirweb.org. Thanks for tuning in and have a great day, everybody.